We all run programs hundreds of times a day without giving it a second thought. But what's really going on under the hood when we do? Let's pull back the curtain and find out.
You know, you tap an icon, and just like that, an app opens. It feels like magic, doesn't it? But it's not magic at all. It's this incredibly high-speed, microscopic dance of logic and electricity. So what's actually happening? We're going to trace that entire journey, from your tap all the way to the computer's final action.
So, the first big hurdle is a language barrier. I mean, a huge one. We write ideas in languages that we can understand. But computers, they only speak one language, the language of on and off, of ones and zeros. That's it. So every single instruction we give has to be translated.
This journey from human speak to machine speak happens in stages. We start with what's called a high-level language, like Python or Java, which is designed to be pretty easy for us to read and write. That gets translated into assembly, which is kind of a middle ground language. It uses simple words like LDA for load, getting us a lot closer to what the hardware gets. And from there, it's finally converted into the real deal, pure binary machine code that the processor can execute directly.
Now, why does this translation process even matter? Well, it has huge, real-world consequences. Just take this quote from a Facebook engineer. He explains that a language like PHP is great for getting ideas up and running fast, but for something massive like the newsfeed, where performance is absolutely critical, they need a language like C++ that translates more efficiently and gives them direct, hands-on control over the computer's resources.
So how does this translation actually happen? Well, there are two main ways. First, you've got a compiler. Think of it like a book translator. It takes your entire program, converts all of it into machine code in one go, and creates a new standalone file you can run. This is generally way faster. Then you have an interpreter. This is more like a simultaneous translator at a conference. It reads and executes your code one line at a time, on the fly. It's more flexible, but yeah, often a little bit slower.
Okay, so once our instructions are translated into that pure machine code, where do they go? They get sent straight to the brain of the operation, the central processing unit, or the CPU. This is where the real action happens.
Inside the CPU, the first key player is the control unit. The best way to think of it is as the ultimate traffic cop, or maybe an orchestra conductor. It doesn't do the math itself, but it directs the flow of every single instruction, fetching them from memory and telling all the other parts what to do and exactly when to do it.
Next up is the Arithmetic Logic Unit, or ALU. This is the pure mathematical brain of the CPU. Anytime your program needs to add two numbers, or check if one value is greater than another, or do any kind of calculation or logical test, the ALU is the component that rolls up its sleeves and does the heavy lifting.
And finally, there are the registers. Think of these as a tiny, super-fast notepad that's built right onto the CPU chip itself. They hold the exact little pieces of data that the ALU needs for its very next calculation. That incredible speed is a huge part of what makes modern computers feel so snappy. Okay, so we've got our translated code, and we've met the main parts of the CPU. How do they all work together? Well, they all operate on a constant, powerful cycle that is literally the fundamental heartbeat of all computing.
It all boils down to a constant three-step dance: fetch, decode, execute. First, the control unit fetches the next instruction from memory. Simple enough. Then, it decodes that instruction to figure out what it's supposed to do. And finally, it sends the command to the right component, like the ALU, to be executed. And this isn't happening once or twice. This cycle repeats billions of times every single second.
A really great way to remember this is to think of it like following a recipe. First, you fetch the next step by reading it from the cookbook. Then you decode it by figuring out what chop or sauté actually means. And then you execute it by actually chopping the onion. Your computer does the exact same thing, just, way, way faster.
Now, this all sounds very neat and tidy, but what happens when something in this microscopic, ridiculously high-speed process goes wrong? Well, the consequences can be massive, and that's exactly why understanding this foundation is so important.
I mean, even a single misplaced bit, just one incorrect 1 or 0 in a single instruction, can cascade and snowball into a complete system failure. The stakes are incredibly high.
Let me give you a real-world example. In 2018, a major Canadian bank had its online system go down completely. The cause? A tiny software bug. That one flawed instruction, processed through the fetch, decode, execute cycle, was enough to grind the entire system to a halt and lock thousands of customers out of their accounts. It's a stark reminder of how critical every single step is.
And it's not just banking.
A major airline had its entire reservation system go down across the globe. Flights were grounded, travel was thrown into chaos. And the root cause? A failure deep inside the computer's instruction processing. It really shows you just how much our modern world relies on this fundamental cycle working flawlessly, billions of times a second.
So, we've gone on a journey from a simple tap on an app, down through the layers of translation, and right into the lightning-fast heartbeat of the processor. Understanding all this isn't just theory. It's the foundation for debugging tricky code, for squeezing every last bit of performance out of a machine, and ultimately, for just building better software. So the next time you tap an icon, maybe you'll think about that incredible microscopic dance and start to wonder, how could you make it even better?